I'm sorry, this is problem number 10. And it has a sign that's been hung with 2 cables. So here's our sign and 2 cables. One of the cables makes an angle of theta with the roof line, and the other one is perfectly horizontal. The sign is mass M, and we're asked to come up with a relationship for the tension in this cable based on this angle. Does that narrow it down? Now, the wording of the problem, I'm sure, is a little bit different than that. This is the start of what I would say is probably a decent AP level question, but probably multiple choice. And what I want to impress upon you is the difference between what the force concept model can give you and what you have to actually do to solve the problem. The force concept model only leads you to a place where you will have information, and that information may or may not be applicable to answering the question. So I want to keep in mind that if you believe that using the force model is the way to go with the problem, then know what it's going to provide for you. If you're faced with a question like this, they're asking you to find one of the tensions in terms of something else. They're also stipulating that your answer can only have certain things in it. This is probably all that's going to be able to be in the answer. I'm bringing this like most of your problems are never going to have a number in them. You're going to be developing an expression. Numbers are in your homework a lot because you need to practice, and having a number means that there's an answer, but most of the AP exam is going to be a series of expressions, and you're going to have to kind of figure out at the end whether your expression fits what you would expect it to fit or not. So this is a problem in which you're going to need an expression. But to do this problem, you're probably going to have other variables that currently aren't here. So, for example, I'm going to write that this is TR, meaning it's a tension in the right. But I know there's also a tension on the left string too. They're not going to be the same. So I'll start the problem where I suggest you start, which is a free body diagram, to help lay out the forces acting on the object. And for that, I'm going to have a downward force for weight. There's going to be a purely horizontal force. I'm not going to draw that one yet. I'm going to draw the one that's at an angle. And I'm trying to be cautious here. This size should be the same as this size. This is the only cable that pulls upwards on the box. It is supporting the full weight of the box. So it has to be long enough in the Y direction to provide the same size force as the weight is pulling down. If you're trying to draw your picture accurately, and at this point we're moving beyond just are the arrows in the right direction. So if you're trying to draw your picture accurately, there should be some attention spent to making sure your arrows are to scale. The next arrow then has to scale left and right and be about the same to the left and to the right. So labeled correctly, this is T to the right, this is T to the left. I'm going to put a coordinate system in. I think the clear and obvious choice is one that's lined up with TR and MG. So I'll make that the positive X direction. This is the positive Y direction. I have one vector that's not lined up with the rest, but before I start attempting to work on it, I need to figure out where to place theta so that it fits in the scheme of what I've drawn. It's going to go here, and I know that because if I drew a horizontal line up there mimicking the ceiling, this line and this line are parallel to each other. This is a transverse cutting across 2 parallel lines. These angles are alternate interior and therefore have to be equal. So this is how you apply your geometry here. So I've sat with some students after school talking about their geometry. That's what I talk about when I say you need to know your geometry. So with that, I can take and break my vector up into a, let's see, TL cosine theta, horizontal one, and TL sine theta, the vertical. All right. I'm on the last step, which is to take net force in the x direction, set it equal to 0. Net force in the y direction, set it equal to 0. In the x direction, I have two vectors. So it looks like TR minus TL cosine theta would be equal to 0. In the y direction, I have two vectors. So it looks like TL sine theta and mg. So TL sine theta minus mg equals 0. All right. That's all that the force concept inventory can do. It can produce two relationships for you. Whether you can use those relationships to get to the answer or not, that's now on you. But it gets us here. So any question about using the force concept model to get to this point? All right. The next part of the problem begins here. Can I use these two things to get an expression for TL in terms of variables that are allowed to be in my problem? I am not allowed to have, TR. I'm not allowed to have TL in my answer. So I need to find a way to eliminate TL. Substitution is probably the best way here. I can solve for TL on one side and plug it into the other. I'm going to do it a little different just because whenever I see TL cosine theta and TL sine theta, there's ways to kind of work this out faster. However, before I do that, I'm going to write this as TL cosine 30 equals TR, and TL sine 30 equals mg. I'm going to stack them like this because I can divide both sides, and that immediately gets rid of TL on the left side and gives me tangent. I'm not sure why I put 30 there. I guess because I'm still thinking of the last example. It should be theta. Tan theta equals mg over TR. You're supposed to solve this for TR, so TR equals mg over tan theta. This is the answer. This is TR in terms of the angle and the mass of the object. Does it make any sense? There's ways we can test it. What is TR when theta equals 90 degrees? You guys know things. What is TR when theta equals 90 degrees? You'll have to find the tangent of 90 degrees. Your calculator is going to be unhelpful here because you're going to say words like undefined. But you're sharp people. Think it through. Tangent is sine theta over cosine theta. Sine theta, sine of 90, is 1. What's cosine of 90?
0.
So as we approach 90 degrees, tangent theta approaches, doesn't approach undefined. What does it approach?
0.
No. Way to go. But it does approach infinity. It's 1 over 0. So as we get closer and closer to 90 degrees, tangent gets closer and closer to infinity. mg over infinity means that TR, as theta goes to 90 degrees, is 0. Because we're taking mg and dividing by infinity. This is the kind of thought process I'm going to expect of you. That makes sense. Because look at your picture. As this goes to 90 degrees, we are just hanging the box. Do we need TR at all? The right cable is not holding the box any longer. So that makes sense. That's a reasonable outcome, that TR would go to 0 when theta goes to 90 degrees. This is how you test your outcomes. Test this one. What's TR going to be as theta approaches 0 degrees? You need to know what tangent of 0 degrees is. This one's easy. What's tangent of 0 degrees? 0. What happens to this function as the denominator gets closer and closer to 0? Can you divide by 0? Can you divide by a really small number? So that means TR gets bigger and bigger and bigger as we attempt to make this angle equal to 0. Can that angle ever become 0 under this circumstance? Can't. It means no matter what, if you try to hang something, you can never have both cables be perfectly horizontal and hang something. There's no component that pulls upwards. So this will never work. All right? There has to be some angle here. There has to be some component of the force upwards to balance the weight. So there is no way to get this to ever happen, right? Without having infinite tension. These are the kind of tests you're going to have to do. And your silence bothers me. Because if you're not able to just think of these ideas, it's going to be harder and harder for you with our next couple of examples. All right. Well, if all you care about is what the answer is, Gabby, that's the answer. All right. Or can I just do the free body diagram? That's good. I'm glad. This was one of our examples, I think. So I have weight of the lawnmower. It was said in the problem that the weight of the lawnmower is 250 newtons. 25 kilogram lawnmower, 250 Newton lawnmower. There's a 100 Newton force at an angle of 30 degrees downwards. And I think we have two other forces. Normal force and a frictional force. They are all balanced because the lawnmower is traveling at constant velocity. Any questions about the choices I made here? All right. I'm going to choose a coordinate system aligned with the ground and gravity. I'm going to take my 100 Newton force, knowing that this is 30 degrees, and break it up into a force that is horizontal and a force that is vertical. That will be 100 cosine 30, which is 86.6, and 100 sine 30, which is 50. Any questions? All right, well, there are three forces in the y direction. So net force in the y direction equals 0. I have normal minus 50 minus 250 equals 0. So it looks like normal equals 300 newtons. Net force in the x direction is also 0, and that's going to be 86.6 minus friction equals 0. So friction equals 86.6 newtons. The coefficient of friction is the percentage of the normal force. So friction equals a percentage of the normal force. This is what we mean by coefficient of friction. So I just need the ratio of friction to normal force to get the coefficient. The symbol we use is Greek letter mu, which we'll get to today, but that's it. So 86.6 divided by 300. It's a unitless value because it's a percentage. Okay, so the bird on the cable problem is, there's a couple things about the bird on the cable problem that you have to kind of, I don't know, come to grips with, I guess is a nice way to put it. So bird head, bird beak, bird wing. Okay. So the bird's on a cable, and the cable is a meter on each side. It's kind of what I got as the setup of the problem. Trying to make it look symmetrical. Does that look pretty symmetrical to you guys? All right, so the cable has only one tension in it. This is this is something we'll talk more and more about, but it acts as though it's pulling in two directions on the bird, as if there's a tension this way and a tension this way. The two tensions are the same, but they act in opposite directions on the bird. The bird, of course, has a single force downwards in the situation of weight, and the combination of the two tensions and the weight brings the system into balance. Now, I probably should make the weight smaller because the bird only weighs a couple grams. So weight of the bird, tension and tension. Good? Any question about the way I've set this up? I've kind of drawn this as a free body diagram on purpose. So I can place my coordinate system right over the top of it. With this being theta and this being theta. They didn't give you theta, but they gave you the information that you could use to find theta. They told you that this was 1 meter long and that this was 4 centimeters. That's enough information for you to find theta. Everybody got that okay? So I'll leave that part to you. I'm going to do the work in terms of theta. So knowing that's true, I will say this is a net force equals 0 problem. And breaking this up into positive x and positive y, I think in the x direction, I have a portion of the tension. Jeez, what a mess. I can't even talk and do this at the same time, I guess. I have a portion of the tension that's this way, and I have a portion of the tension that's that way. Right? I'm taking my tension and breaking it up into its components. The horizontal component will be t cos theta, and the vertical component will be t sine theta. All good so far? All right. The other side is symmetrical. So I think if I do it once, I've done it twice. Is that okay? So although I'll write out net force in the x direction, that's really not going to help me because it's t cosine theta minus t cosine theta equals 0. So that's a big duh. But there it is. I'm just following through with my set of steps. Sometimes a step yields a particularly useless piece of information. Net force in the y direction also equals 0. That'll be t sine theta plus t sine theta minus mg equals 0. Now that's really the end of the problem once you get theta, because this will be 2t sine theta equals mg, or the tension is mg over 2 sine theta. I don't remember everything about it, so I'll do my best. There's a box on a ramp is my recollection. And it's going to experience a horizontal force. So let's get this and change the ramp, but it's being pushed up by a horizontal force, meaning the force is horizontal to the compared to the ground. So this is the direction of the force on the box. Does that make sense? And the box has weight, of course, and there's others. So I think there's a coefficient of kinetic friction between the box and the ramp. This is another way of saying the percentage of friction. So if we were saying that friction is a percent of the normal force, then we will replace the percent with this little symbol called the coefficient of friction. I believe that's represented in one of the questions earlier, saying that don't be scared off by coefficient of friction, it's just a percentage of the normal force. Formally introducing the symbol here, Greek letter mu, we're using the lowercase version of mu. So if A is like that and P is like that and a U looks like that, mu is written like that. Typed, it tends to have a straight tail or whatever you call that little hangy down thing. There's names for them all, but I don't remember them. So when you write it like that. Part of the reason I show you guys this is because you will have to write these symbols as they're supposed to appear, or your grader will not necessarily give you credit. Friction equals mu times the normal force. It should look like that. Every year I have people who write this. That just looks silly. You guys understand why I'm saying it looks silly now? So when you're trying to write these things, please try and write them accurately. Your test grader has to believe you know what you're doing. And every time you do something like this, you give them pause to think maybe you don't know what you're doing. Is that good? All right. So let's go ahead and move through this problem. My understanding is that we're trying to find an expression for the applied force that will allow the box to go up the ramp at a constant velocity. So what I believe we're being told is we can have m in our answer, theta in our answer, mu in our answer, and g in our answer. I'm bringing this up because there are lots of forces acting on the box, but none of that can be in your answer. These things can be in your answer. So I need F equals something that has these things in it. Does that make sense so far? Well, the force concept model doesn't give you the answer to this problem. The force concept model may give you some information that could lead to the answer to this question, but doesn't give you the answer to this question. Let's start with a free body diagram. So I'm thinking weight first. And then we have, of course, normal force. Then we have friction. And then we have this applied force. So F, mg, friction, normal. Are these our four forces? Yeah. That's question 6. Right, and 7 adds a coefficient of friction, doesn't it?
Oh, my bad.
Did you ask for 6? I'll be happy to perform 6.
No, don't worry.
Okay, so this is what you want to see?
Yep.
Okay. The first thing I want to kind of point out is that I see 2 possible places to put my coordinate system. Do you? If I do the coordinate system in terms of where the weight is, well, that would be lined up with 2 of the 4 forces. I could do the problem this way. Or I could do the problem this way. I have to pick one of these. The net force equals 0 no matter which way I pick. Now, both ways will give us the same answer. The real question is, which one should we choose? I'm saying this not in an unrelated way. I'm saying that one of these choices actually is much harder than the other. But it's hard for you to know which of those 2 choices is the harder choice to make because of lack of experience. So I will say that no matter which of these choices you make, you can get to an answer. But here's how you kind of decide which set of coordinates would be the best ones. Because I think most of you will probably just work autopilot. It's an incline, we're going to do the blue ones. But there are times where doing the red ones would be better, even if it's an incline. So it's not always as cut and dry. Here's what you need to consider. We will not be able to have friction in our answer, and we will not be able to have normal force in our answer. Now, the reason I'm bringing that up is because we can't have either of those in our answer, if we choose the red coordinate system, friction and normal force will have to be broken up into their components. They will appear in 2 different places in 2 sets of equations. they might be harder to deal with if done that way. Remember, we're going to have to get rid of them. We have to substitute them out somehow. It'd be easier on you if they appear less often since you're having to do substitution. Does that make sense? So I would encourage you to use the blue coordinate system and not the red coordinate system under this circumstance, because we're going to try and get rid of any reference to friction and every reference to normal force. And the fewer times they appear, the easier it is to do that. So the blue one it is, whether you understood that argument or not. We're going to use the, I don't want to take all that away. We're going to use the blue coordinate system. There we go. That means I have to break up the weight and the applied force. This angle here is theta for both of them, for the same reasons why we talked about that yesterday. I'm going to have those two as my components for the weight. That'll be mg cosine theta and mg sine theta. Once I get those in there, I do not need to have any representation by mg by itself. So I have people who, for whatever reason, kept putting mg in their answers for some reason. It was weird. But mg's gone now. It's going to be mg cosine theta or mg sine theta. And the applied force is going to have F cosine theta and F sine theta. All right. Any questions about breaking them up into components? Net force in the x direction equals 0. Net force in the y direction equals 0. X direction, I see three forces. I see friction, mg sine theta, and F cosine theta. Those are in the x direction. I'm going to make the right positive. So when I do, that gives me F cosine theta minus mg sine theta minus friction equals 0. Any question about where that's come from? All right. In the y direction, I have 1, 2, 3 forces. I'm going to make upwards positive. So I will get normal minus mg cosine theta minus F sine theta equals 0. Any question about where that's come from? All right. Remember, the whole point of using the force concept model is to generate relationships that might be able to be used to solve your problem. We've done that. All that other stuff is not necessary for the time being. We have one more piece of information that we can bring to bear in this problem, and that is we can introduce the normal force. I'm sorry, we can introduce the coefficient of friction, which relates the normal force to the frictional force. So we have these, all these pieces. Now, take a pause for a minute and realize what you need to do. We are looking for F, an expression for F. I have to eliminate normal and friction. It can't be in my answer. So I can't solve either one of these for F and turn that in, because it's going to be in terms of something that's not allowed to be in my answer. Everybody follow along? And it's not like I can solve this for F and plug it in here to eliminate it. F doesn't appear over there. And if I solve this for F and eliminate it, that defeats the purpose. So I need to solve for that. So luckily, I have another piece of information. But basically, and this is what I think is hard for students, so hear me out. I have 3 equations and 3 unknowns. That's an unknown, that's an unknown, and that's an unknown. Two of them I have to eliminate. One of them I need the expression for. So I'm going to do lots of substitution. In fact, I'm going to come up with a plan. And there's a couple ways to do this. Like, you could solve this for the normal force and this for the frictional force and just plug them both in here. That would eliminate friction and normal force. Or you could substitute normal force in here, and then whatever you get, substitute that in for friction here. That'll do it too. Which one do you guys want to do? The second one? All right, I'll do the second one. So to do the second one, I need an expression for normal force. I kind of have it, so normal force equals mg cosine theta plus f sine theta. So now my first substitution. I'm going to plug it in there. So friction equals mu times mg cosine theta plus f sine theta. I'll go ahead and distribute the mu. So friction equals mu mg cosine theta plus mu f sine theta. All right, first level of my substitution is done. I've got friction in terms of the applied force. So I have this, and I have another equation that has this and this. One more substitution, and I eliminate the little f. You follow so far? So next, all of this needs to go there. All right, so we'll do that. I'll have f cosine theta minus mg sine theta minus mu mg cosine theta plus mu f sine theta equals 0. Bring that front and center. I have one relationship now that has the one thing I want, and none of the things that I'm not allowed to have in my equation are in the equation. And everything else that's left, theta, m, g, and mu, these are all allowed to be in my answer. So this is where I can go. I can solve this for f. And I highlighted f so we know where it is. So now I'm going to start the monotonous process of solving for f, which begins with distributing the negative sign. You guys see that okay? So I'm going to distribute the negative sign. I can do that probably easier than you guys can. Well, no, some of you have the same kind of stuff I've got. So there, I distributed the negative sign. I'm going to collect the terms that have f in them. So f cosine theta, f cosine theta minus mu f sine theta minus mg cosine theta minus mu mg, I'm sorry, that's sine theta, getting ahead of myself, mg sine theta minus mu mg cosine theta equals 0. I'm going to move both of these to the other side of the equation. That seems like the next step, right? I want to isolate f. So getting everything that does not have f to the other side seems like the next logical step. They're both negative. I know some of you would prefer I do plus mu mg cosine theta plus mu mg cosine theta. And then, I know some of you want me to do that. I know some of you have to do that yourselves to do the algebra. You note that that's probably not something I feel like I want to do because it's just a lot more writing for me. I'm doing it once, mostly to show you that I understand that some of you have to do this because your algebra skills are not where perhaps I would like them to be, but you're practicing, you're getting there, you're trying. But I would have moved them all over in a single step because I think I can. Although some people in the room are wondering, would I ever be able to do this? I sure hope so. We can test next week. All right, we're at the end. We're going over homework. To me, this is not too far out of the question. I could factor out the f now. I have cosine theta minus mu sine theta equals mu mg cos theta plus mg sine theta. So now divide both sides by everything that's in parentheses. That's the answer. How do you know? How do you know that's the answer? It doesn't, it doesn't look, it looks crazy, doesn't it? That's a whole lot of stuff. It's hard sometimes in a complicated problem like this to figure out whether your answer is the answer or not. One thing I would encourage you to consider doing is what I'm about to do. It's not necessary to get the right answer, not necessary to get the right answer on the test, but I'm going to notice that there's an mg and an mg here. Do you see that as well? I'll factor that out. And write this as f equals mg times mu cosine theta plus sine theta, all divided by cosine theta minus mu sine theta. Now, the reason I did that is because one of the things you can do is you can look at units. Units are a good way to figure out if at least what you have there is algebraically correct. I didn't say that the answer made sense. I just said it's algebraically correct. See, mg is the only thing on this side of the equation that has units at all. M is going to be in kilograms, and g is going to be in meters per second squared. Together, those guys are in newtons. Everything in here is a unitless quantity. The sine of an angle returns a percentage. Mu is a percentage. They have no units at all. So I'm taking something that's in newtons and I'm multiplying by a scaling value that has no units. And it has to equal something that also must be in newtons. So it makes, at least at this level, it passes one check. A check that my units will work out, so there is the possibility that this is the answer. Now there are other checks we could run. In fact, one of them is to set mu equal to 0. Then your answer should agree with question 6, right? If there's no friction, then mu is 0 because that would zero out the frictional force. So if you put 0 in for mu, you get F equals mg tan theta, which should have been your answer for question 6. It's just another way to check. These are things you can do to help see if your answer makes sense. But be careful. And I want you to take a look at something. First, this was a lot of work. I was slow doing this problem with you, and we're at 21 minutes. When I say slow, I'm explaining everything, right? I would suspect, for those of you who are thoughtful students, that this would have taken you a long time to do, especially the first time. This is the problem, isn't it? the physics of this problem, the part where we learn the force concept inventory, well, that's everything above that yellow line. Everything after it was algebra, which suggests that on the AP exam, this part, 1 or 2 points, right? There'll probably be a point for recognizing that you have to use mu times the normal force. There'll probably be a point for getting each of these functions. There'll probably be a couple points for using your free body diagram correctly, and probably a couple points for getting the trig right. But then doing your algebra, which probably is the most time consuming, probably a point. However, if you think this is what an FRQ is going to look like, it's not. The FRQ is going to have this as part B or part C. And then there's going to be a part D and an E, maybe even an F. And this all assumes that you knew to use forces for this problem. Remember, the FRQs are going to have all the stuff mixed up. If you can do all of this, you're probably looking at a 4 on the exam. There's going to be some follow-up question, especially for one like this, that turns the problem from a 4 into a 5. And it has to do with this answer. Whenever you get an answer like this that has a quotient in it, look carefully at the bottom part of the quotient and be extra, extra concerned about negative signs in the denominator. If you look closely at this, there's the possibility that you could have a problem with your answer, right? Because cosine theta can't equal mu sine theta. Do you see why? That would give you a 0 in the denominator. And we don't do zeros in the denominator. Do you see that? But that's also telling us something. In fact, I see a question where they ask something about, what is a uncertain or impossible circumstance? And the impossible circumstance is that mu can't equal cosine theta over sine theta. That's just a saying. In fact, this is cotangent. It says that under this condition, there is no force that will allow you to push the block up the ramp at a constant velocity. That's what it's saying. It would take infinite force to do so, because you'd get a 0 here. I don't know what this condition is, but that's what the condition is. It has to do with the angle of the ramp, and it has to do with mu. Now, a couple things about cotangent is cotangent becomes less than 1 for angles that are greater than 45. That's probably something worth knowing, because mu has to be less than 1. So there's going to be circumstances like this. There's going to be some angle and some combination of the angle and mu where you can push all you like and the box is just going to sit there and probably keep going down the ramp against your wishes. All right. Yesterday, I saw this on a piece of paper in this classroom. And the numbers aren't right, but bear with me. It's not about the numbers. Something like this was written down. Except, let me see. There was something else in here, this had to be like F. And they divided both sides by cosine 30. That seems not unreasonable. But then they got in this room there was 3 people who did something like this. 7th period there was a handful, 3rd period there was a handful. Some of you don't know why this is wrong. The others of you know why it's wrong and can't believe that somebody did this. I am the latter of those 2 groups. You're dividing both things by cosine 30, so although you can break it up, you still have to divide both things by cosine 30. I'm going to assume that this is an error that is produced because you're in a hurry, but it's just as wrong.